Hello everyone, I'm Muhammad Taha Ibrahim from the iGravy Lab at the University of California, Irvine, and in this video I will be presenting our paper, Self-Calibrating Dynamic Projection Mapping System for Dynamic Deformable Surfaces with Jitter Correction and Occlusion Handling. Our work is in the domain of projection mapping, which is a technique that uses projectors to map images onto objects and buildings, in this case the Sydney Opera House, and transform their appearance. To understand how it is achieved, let's look at the key problem of projection mapping. Imagine we have a setup where we'd like to project this image of a face onto a curved surface. Doing so, we'll notice that the face appears distorted. Now that is because the surface shape is curved and not flat as is normally the case. But if we were to have information about the surface shape, then we can warp the original image such that when it gets projected back out, the distortions disappear, resulting in a shape-conforming display. And so this is the key problem of projection mapping, determining the surface shape. And so to assist with surface shape reconstruction, we add a camera and perform structured light scanning to establish pixel level correspondences between the camera and projector. These pixel correspondences are then triangulated to recover the 3D shape. But to triangulate pixel correspondences, we need a calibrated projector camera system. Now, calibration in the context of projection mapping refers to computing the pose or orientation and location, and the intrinsics such as the focal length, principal point, and distortion coefficients of every projector and camera in the entire system. Now, calibration accuracy is crucial as errors in calibration can result in an inaccurate shape reconstruction, which then causes distortions and misregistered projection displays. So this brings us to prior work in projector camera calibration, which can be broadly classified by the number of projectors and cameras there are in the system, for example, single or multiple, as well as the type of cameras that are being used, whether they are RGB cameras or RGB depth cameras or RGBD for short. So starting off with single projector, single camera systems, they typically perform structured light scanning and use a known calibration object such as a planar checkerboard or an object with known shape to establish pixel correspondences between the projector camera pair and then calibrate the system. Multi-projector single camera systems also use structured light scanning, but additionally they have prior knowledge about the surface, which they exploit to impose constraints on the calibration optimization. So prior knowledge may be, for example, the surface dimensions, aspect ratio, whether it is vertically extruded or not, and so on. Multi-projector, multi-camera systems also use structured light scanning, but they do not require any knowledge of the surface shape or the calibration parameters because using the structured light scanning, they constrain the calibration optimization through the pixel correspondences and across multiple cameras and projectors and calibrate the entire system. Now, when one or more depth cameras are involved, this allows such systems to use calibration objects of arbitrary but known geometry to iteratively refine the calibration parameters. And so this table here shows a bird's eye view of the prior work on projector camera calibration. Note that all works require the surface to be static and rigid during calibration, irrespective of whether the object moves during the projection itself. So now this is a reasonable assumption unless the surface that you are projecting on is dynamic and deformable. And so no prior work can perform projector camera calibration on deformable surfaces, which is where our work comes in. We present the first work that performs projector camera calibration on deformable surfaces where no information about the surface shape is known or any information about the device calibration parameters. And so now we talk about our contribution. Our setup includes a projector depth camera pair, which we call a PDC, projecting on a deformable fabric. On either side of the fabric, we have two fans that cause the fabric to move constantly and randomly. We begin by projecting a grid of Aruco markers on the deformable surface while the RGBD camera captures the images. We detect the Aruco markers in the RGB image and get the depth at those pixel locations. This gives us correspondences between the projector pixel, the camera pixel, and the 3D point. Next, we perform camera calibration. The RGBD camera is assumed to be at the origin, looking down the positive z-axis. This means we only need to determine the intrinsic matrix and the distortion coefficients. So we do this using a standard nonlinear optimization that minimizes the reprojection error. After that, we perform projector calibration. Now we need to determine the projector pose and intrinsics. However, we have no prior knowledge about any of the projector parameters, and the optimization requires a reasonable initialization to avoid getting stuck in local minima. So we first perform a coarse projector calibration that provides a rough estimate of the projector parameters and use that to further refine the parameters in an optimization. We exploit the surface movement to determine the projector pose. So first we observe that each row and/or column of projector pixels in 2D forms a plane in 3D. So we fit planes through each set of 3D points that correspond to the same projector row or column. Next, we intersect all the row planes, which gives us a line in 3D. The direction of this line corresponds to the projector's x-axis. Similarly, we intersect all the column planes to get a line whose direction is the projector's y-axis. And the cross product of the two gives us the projector's z-axis. Intersecting all the planes, the row planes and the column planes, gives us the projector location. And now this gives us a rough estimate of the projector pose. Using that and the 2D to 3D correspondences, we can compute a rough estimate of the projector intrinsic matrix, assuming no distortion. So finally, we feed the results of the coarse calibration to the optimization that aims to minimize the reprojection error. Here is the final camera reprojection error as a function of the surface speed for different projector types using our calibration method. Here is the projector reprojection error as a function of the surface speed for different projector types using our calibration method. Note that due to noise in the depth camera, we do see a higher error with increasing surface speed. And here is our dynamic projection mapping system that uses our calibration parameters. Our calibration parameters are very accurate even when the dynamic surface moves outside the original calibration volume as shown in the photo below. We also studied the effect of depth variation on the projector calibration accuracy. Note that having a variation of 7 millimeters or more results in excellent calibration. Now, a problem with using depth cameras for dynamic projection mapping is jitter in the projection due to depth camera noise. So we propose to use a Kalman filter to smooth out the 3D trajectory of the points used for rendering the projection display. Here are the results. Another problem is handling occlusion of the surface. We use the Kalman filter predictions to replace any occluded points and then compute a rigid transform to account for any global movement. For more details, please refer to the paper. Here are our results. And so in conclusion, we propose a method to automatically calibrate a projector camera rig using a dynamic deformable surface without any knowledge of the surface shape or the device calibration parameters by exploiting the surface movement. We also propose a method to handle jitter in the projection mapping as a result of depth camera noise and handle occlusion of the projection surface despite rapid surface movement. Thank you.